as Scott said, I will be talking about solar fuels and a systems view on this very challenging problem. So this is going to be the outline of my talk. I'll start with some background and motivation. Then I'll briefly go through some of the methods that we had to develop to study the system, and then I'll go to the results. I'll talk about energy efficiency and how the energy efficiency of such systems can be improved. Some results about the economics of such processes, and then depending on how much time we have, I'm going to touch on some of the extensions, which are a little bit more technical. So we're in a sustainable energy seminar, so I'm not going to go through why we need to study renewable alternatives for energy and power production. The only thing I'm going to say is that the challenge is there. CO2 emissions increase, the CO2 concentration in the atmosphere increases, and this has some unintended consequences. So many different technologies have been proposed to address these challenges, and probably it's not going to be a single technology that is going to be the answer to this very, very daunting problem. It's going to be multiple technologies. And in this context, solar fuels has been relatively recently proposed as one such technology. So what's the motivation for studying solar-based fuels? Well, the motivation is that really solar energy is widely abundant. And here are some interesting statistics. The energy intercepted by the Earth in 1 hour, it's more than the annual consumption worldwide. But this has certain challenges. So one challenge is that really going from solar energy to chemical energy in the form of a liquid fuel has very, very low efficiency, and I'll discuss some of these numbers. And then solar energy is not, I'm saying here, is not uniform. That comes in different flavors. It's highly distributed in terms of geographic availability. We have seasonal variation, and also we have intermittency. So even in the summer, even during the day, even in Arizona, we may have some clouds, and this poses some challenges. So what we would like to do, what we do in our lab, and what I'm going to be presenting today, is really start to understand what are the major drivers in converting solar energy into liquid fuels, and what can be done to address some of these challenges, and really how to address these bottlenecks, and ultimately guide future research efforts. So again, this is a map, but even a red area doesn't mean that building a facility that will convert solar to liquid fuels in an area where solar energy is very high, it's trivial. Okay, so just to put things a little bit in context and what specifically we will be studying today, I'll say that there are different ways to go from solar to liquid fuels. So one way, and I would say the pathway that today is the most promising, is the following. We convert solar energy to electricity, and now in each one of these blocks, I'm going to have some numbers which are approximate efficiencies for a given conversion. So we can go from solar energy to electricity, and then once we have electricity, we can use electrolysis, which is a technology that has been studied extensively. Its efficiency is quite high, and that would give us not exactly liquid fuels, but it would give us hydrogen, for example, and we can use hydrogen to go to liquid fuel. So probably the overall efficiency is not going to be as high as 7%, but close to 7%. But the solar fuels are going to be utilized, so the liquid fuel is going to be utilized in a diesel engine or in a gasoline engine, which approximately has 30% efficiency. So if we multiply all these red numbers along this pathway, we're going to go from solar to energy energy like on the wheels. The overall efficiency is going to be 7%, which is low, but actually is the best today. Okay, and this really illustrates some of the challenges for going from solar to transportation energy source. Okay, now let's say challenge with this pathway is that once we have electricity, it's probably better to use it directly in an electric motor. So if we have electricity and we go to storage with batteries, and storing using batteries has its own efficiency, so we're going to have a heat there, but finally use it in an electric motor or of a hybrid car or an electric car, then the overall efficiency is better, is 20%. So what we learn from this very simple analysis is that once we produce electricity, renewable, then probably it doesn't make a lot of sense to convert it back to a liquid fuel to use it in a car. It would probably be better to go electric all the way, and this would have a better efficiency. So today we're going to be studying an alternative route, but again, another lesson from here is that probably today the best thing to do is electrify as much as we can. So use solar to produce renewable electricity and then electricity in electric cars directly. But liquid fuels are needed. So trucks, planes, it's going to be many years before we trust that we can have batteries to operate these larger vehicles or have just batteries in the air. So we need liquid fuels. So what we decided to study here is what would it take to have a process that would take us from solar to liquid fuels directly, chemically. So with the chemical conversion, we would convert solar energy to liquid fuels, so that we have efficiencies in the 3 to 5% range. So today, really, I'm going to be talking, what does it take? That's the question mark here. What are the technologies and what we should be focusing on in order to materialize this? Okay, so I'm talking about solar, but the liquid fuel needs carbon. So where is the carbon going to come from? So carbon potentially has multiple sources, and this pie chart really shows CO2 emissions by sector in 2011. And what we're going to assume for this study is that we are going to use what we call a point source of carbon, a power plant. So a power plant, we generate electricity, but you have CO2 emissions, regardless of whether we use coal or natural gas. The idea is to use this CO2 and using solar energy, convert it into liquid fuels. So that's the idea. And I'm going to show here a little bit into the details. It's not straightforward to as we say, separate CO2 from a power plant. For the non-engineers, very like 1 minute overview. So we have natural gas or coal brought into a power plant, and if we consider that the power plant is a big block, this big block produces electricity, but also produces a stream that has CO2, carbon dioxide, and a lot of nitrogen. So we have to separate CO2 from the nitrogen, because nitrogen is what we're going to finally release in the air. We don't care about nitrogen, but we care about CO2. Doing what I just described, separating CO2 from nitrogen, is not trivial. It requires energy. So this is very important to keep in mind, because really what we're trying to do is come up with a renewable energy. If we're going to spend a lot of energy to do so, then we defeat the purpose. Okay, so I'm not going to go through the details. The important things to remember is getting the CO2, which we're going to use with solar, to go to liquid fuels requires energy. Okay, so the idea, and that was a part of a research project, is to have what we would call solar refinery, analogous to an oil refinery. What are going to be our resources? Solar energy, and then the flue gas, the emissions coming from a power plant, plus water. So we're going to pipe in CO2. How we get there is not that important, plus water. This is the boundary of our solar refinery. We're going to use solar energy for two things. One is to carry out these transformations that I'm going to describe very briefly later, but also to generate electricity that we're going to need in our solar refinery to drive different operations. Or we're going to need heat. We don't want to be burning natural gas in our solar refinery, in our renewable refinery, to do that. We would like the heat to come from solar fuels. Okay, so let me go a little bit into the methods that we develop and what really means to study a process a process, a transformation process in general, in this specific case, solar fuel. So this is the idea, and these blocks represent the major operations that we would need if we were to develop solar technology. So we will need to capture and transport CO2 from the power facility, then plus water, and the water is readily available, so we don't worry too much about it. CO2 plus water, which do not have a lot of energy. Actually, CO2 and water are the products of a car that is burning fuel. So the fuel comes in, we burn it, we obtain energy, and then we return water and CO2. These molecules do not have a lot of energy. And the idea is, in a way, to reverse burn, but use solar energy for this reversal. So we're going to start from the products of combustion plus solar energy, and I'm going to be using the yellow to illustrate that this block is carried out by solar energy, and gray for the other blocks for which we don't use solar energy. This conversion, as I will show in this in next slide, is really at its infancy. So it's not that we can convert all CO2 and all water to our fuels, only a small fraction of it, which means that what I have coming out of this block is some of what went in, some of my raw materials, because I couldn't convert all of them, the products, and some oxygen. So that's the idea. And since I really am interested only in these products, not on the other things, I will have to have some other process, and we're not going to go through the details, which would allow me to separate and really recover the fuel, the liquid fuel, which is here denoted like this. Okay, so that's what seems to be a reasonable approach towards the production of solar fuels. The challenge is that what I described here is really at its infancy. So this is the reaction that we're envisioning that is going to be happening, CO plus water going to methanol. This is our liquid fuel. But what is out there available allows us to convert only 5% of what goes in. And it's not that only this thing is happening. Some of the CO2 is converted to something else, not methanol, which is the liquid product that we want to burn in the car. Okay, so let's see what happens in terms of energy. The answer is that the energy that we consume to run this very simple process is 20 times higher than the energy that we obtain in the form of methanol at the end. Now, why is that? And so if we normalize everything and we assume that we are producing 1 kilogram of methanol per hour, the energy content of 1 kilogram per hour of methanol is around 23, and I don't know if I have the number, kilojoules, and the energy that we spend is so much bigger. Well, what happens is that to capture CO2, we need to consume energy. And since only 5% of the CO2 that we are capturing is going to be converted into a desirable product, the remaining 95% is going to be released in the atmosphere. Energetically, we are at a disadvantage because we spend a lot of energy to capture, but then this does not lead to final product. So, but that's okay. We can do things to improve this process. What can we do? Well, again here the color, it corresponds to a different block. So the black color, all this is the energy required to capture 100 units of CO2, and then these other blocks correspond, these other colors correspond to the other blocks. What can we do? We can use recycling, and this is a big thing in chemical engineering and renewable energy systems in general. We want to use every single drop of our raw material or of our energy, of our resources in general. So what we can do? Well, we can have multiple of these blocks where we carry out separations. And by doing so, first, we are going to recycle the CO2, which was very difficult to capture. And we will also recycle water, which is our other raw material. So now, if we see the entire system as a big block, we don't lose CO2. So that's how we start building better systems, by considering these recycles. What I will say, though, is that carrying out these separations also requires energy. Maybe not as much as capturing CO2, at a power plant, but still requires energy. So we have these interesting trade-offs that we're going to start studying how increasing the complexity of the process, how improves some of the metrics, but on the other hand, for example, increases capital cost. Okay, so what I'm going to show next is exactly the same energy analysis for this modified system. What are the changes? The changes is that I have added some additional blocks, right? So now we have some more colors. The D group, the D block was not there before, and the C block were not there before. So we have these new colors. We are carrying out additional separations. So from 0, in terms of these two blocks, we went to a non-zero number, but the energy required to capture CO2 has gone down dramatically. Because since we don't waste CO2, now we have to capture much less CO2 per kilogram of methane. Okay, so still though, this number, which is the production of our, so to speak, renewable fuel, is much less than the energy that we have to spend to run this process. What can we do? So now we will try to address the question that I raised earlier. What are the drivers, the main drivers, and what are the areas where fundamental research can help us in order to address these challenges? So, the only thing don't worry about all the details. The only thing I'm going to say is that there are 3 or 4 key parameters that are going to, at the end, dictate how good the process is. And these are shown in this in red. Is given a flow of CO2 going into this block, how much do I convert? And how much of CO2 and how much of water do I convert? These are 2 important parameters. And I don't think that these recoveries are not that important. And also, we are going to study selectivity. Again, we go with CO2 and water, but some of this CO2 and water is not going to become methanol or liquid fuel, is going to become something else, and this turns out also to be important. So what I'm going to be showing in the next slide is how the overall energy efficiency is going to change as we change some of these key parameters. Now, before I do that, I'll very briefly introduce some of the metrics that we're going to use to evaluate these processes. So, how we do that? At a very, very high level. This is a very nice picture, but a real process would be much more complicated than this. How do we simulate these real processes? This can be done by what is known as process simulators. So we start building a model that would represent reality as close as we can. This can be done through software. I'm not going to go through the details. I'll just say, this would be a screenshot of the software that would, so this would be the process that would correspond to this nice block. But I'm not going to be showing this diagram. I'm going to be showing the simpler diagram. Now, once we have built this model, we can start calculating some interesting variables. So, the result of running this simulation would be that we are going to have some flows, temperatures, and pressures. So we're going to use these variables to calculate some other metrics. So these, I would say, are more like primitive metrics. The software would tell us in every single stream what is the flow, kilograms per hour, what is the temperature, what is the pressure. These are not very interesting. There are too many numbers. We want to calculate something simpler. What do we want to calculate? Well, from this number, material flows, temperature, pressures, and also how much heat or electricity we need to carry out a step, we are going to calculate, and there are methods available for that, the size and the cost of equipment. So this will find, and then from this capital investment has multiple components, how much it will take us to do the engineering for the facility, what would be the overhead, how much we would pay for the land. Very detailed calculations, but they are not very important. At the end, we are going to come up with a total capital investment to build a facility like this, or an estimate of a total capital investment. Okay, this is a one-time cost and is going to be important, but that's not the only cost. The other cost is what I would say we pay day to day. So again, from these flows, temperatures and pressures, we can calculate how much raw materials we need, how much heating we would need, operating labor, and many other cost components, which finally will give us total expenses. And these are the, again, day-to-day expenses. So now combining these two, we can calculate a total cost. And the metric I'm going to be using is what we call the minimum selling price. The minimum selling price, in this case is methanol, our product, is the price at which we have to sell our product to break even. Okay? So, I'm not going to be showing the calculations, but you can think of it that we are starting a process with given parameters, we come up with a cost, and then we adjust the price of our product so that revenue equals cost. So the higher this minimum selling price is, the worse the process. We want a low minimum selling price because that would mean that we break even at a lower price. Ideally, we would like our minimum selling price to be at least, at most, the industrial price, because that would mean that we can compete with the current practice today. It's not going to be that low, unfortunately, but that's also why we do research. We're not there yet. Okay, so again, what I will be reporting is minimum selling price, and this is the price that makes revenue equal to total cost. Okay, so this is the metric that we are going to be using to evaluate the economic feasibility of the process. We also need a metric to evaluate whether energetically makes sense. So here we're going to be using an efficiency, something like an efficiency. So at a very high level, what we have flue gas going in, methanol coming out. We want the energy content of this guy to be higher than what energy inputs we use to run our process. Okay, but and something that's very often is not done is that to produce heat and electricity. So this energy content in the form of liquid fuels is not the same as electricity, although in terms of whatever units of energy, joules may be the same. To produce electricity, we have to burn liquid fuels. So really the comparison that we would like to carry out is the following. The energy content of this stream, which is methanol, how does it compare with the energy content of the fuels that we would burn to generate electricity and heat to run our facility? And as you can see, the efficiency of going from liquid fuel to electricity is not 100%, it's nowhere near 100%. So our liquid fuel should be more than this. Okay? Now, and for this analysis, we're going to assume that the solar energy we use for this conversion or to generate heat and electricity is for free. From an energy point of view, we're going to consider that solar energy is free. So what is the metric? Is this ratio is high heating value. This stands for high heating value, but you can view it as the energy content of the product minus the energy that we consume to run our facility. This is the net renewable energy divided by the energy content of this guy. This should be positive. Okay? If this, so this efficiency can become negative, so it's not really efficiency if this guy is greater than this. So if it's negative, it's not a good process. If it's positive, it's a good process. That's the metric. Any questions? This kind of concludes the little bit the framework about this study. We're going to go to results next. Do you have any questions so far? So minimum selling price is one indicator. This energy incorporation efficiency is the other metric. we will start with energy because a system has to be energetically feasible before it's economically feasible. We should be producing more energy than we're consuming before we start thinking about economics. So I'll go directly to the results, or maybe just I'll say one last thing. For the economics and the energy requirements, we develop some models that we can very easily tell us each block how much energy we require and how much expensive it is. Okay, so.
Actually, I got a quick question.
Yes.
So is that the same metric as kind of energy return on investment, for energy return on energy invested?
Yeah, it can be viewed. It tells us the same. It won't be the same number, but it gives us the same information. So this is our base case. So we are converting only 5% of CO2. 40% of this goes to methanol. 60% goes to methane. It's a fuel, but not liquid fuel. So that's why we view it as a byproduct. And then the reference is 1 kilogram of methanol. Everything is going to be normalized with respect to 1 kilogram of methanol, and this is the amount of energy, megawatts, that 1 kilogram of methanol has. So I'll just repeat, this is where we are today, 5% conversion. Obviously, this is not good enough. What can we do? One obvious thing would be to develop to do the fundamental research that would allow us to develop catalytic systems or other systems that increase that conversion from 5% to a bigger number. So this graph, it has a lot of information, and many of these graphs are going to have a lot of information, but I'll try to explain. This graph shows how the energy consumption of the different subsystems changes as we improve the conversion. So currently we are here, and so we have to add these points to get to the total energy required, and this is going to be 20 times more than the methanol, the energy in methanol. But as we start improving this one-pass conversion, these subsystems start requiring less and less energy, so overall our system becomes more efficient. How efficient does it become? Well, this is shown in this dotted line, which is the energy incorporation efficiency. So really what is happening is that if we go to this, as we make this block more efficient, so we convert more CO2, everything else becomes smaller because we don't have to process so much and recycle so much CO2. So everything gets better, right? Because we have a lot of methanol here, no need for these units to consume a lot of energy and to be very big. Finally, as we approach 60% of conversion of CO2 that goes in, these lines kind of plateau, and what becomes the most important subsystem is the black line, which is the CO2 capture and transportation. So improving conversion, again, for the researchers that are doing fundamental research, is key, is going to make all these subsystems much better, but it won't address the challenge of CO2 capture. We would still have to capture the CO2 to convert it to methanol, and capturing CO2 is energetically expensive. That's what this figure says. Notice that even at 60%, we are just a little bit negative. We don't break even yet. So one-pass conversion won't do it. What about improvements in two areas? Conversion and selectivity. I'm going to drop this. So this graph now is like a heat map. So the y-axis is, we have x and y, two independent variables, and the energy incorporation efficiency is shown as with colors. So as we improve one-pass conversion, this is the total primary, this is the total primary energy that what we have to consume to produce 1 kilogram of methane. So the important number is below. In this area, we would produce more energy in the form of methanol than what we consume. And we can be in this area either by simultaneous improvements in one pass conversion and cost of capture. So again, before we identified as the cost for capturing CO2 an important component. So one could envision basic research advances leading to better ways of capturing CO2. If this can be achieved, we would be energetically feasible in this range. Now, the next question is, well, you are showing these numbers, and these numbers, I don't know, what do they mean? Well, every technology for CO2 capture has an energy requirement. So the state of the art from an economic point of view is what we call chemical absorption, MEA. This is the figure that I showed you at the very beginning. This is the technology that today is the most economically favorable. The bad news about this technology is that it has very high energy requirement per kilogram of CO2 captured. That's why we couldn't become really positive when we were in this range, even with very high conversions. So the lesson from this analysis was that some of the technologies that have been proposed for CO2 capture, actually they have a very important advantage in terms of energy requirements. So absorbents or even membranes would be great because they won't require so much energy. The downside today is that they are very expensive. Okay, so the final thing is how selectivity to methanol would affect the energy requirements. So before, again, the assumption was that only 40% of the carbon dioxide is going to become methanol. What if I process the same amount of carbon dioxide, but I start getting more methanol because the selectivity is higher? Well, this would also lead to some improvements. And this graph shows, so here is the same y-axis. You can think of it as different technologies used for CO2 capture. And here is the selectivity. As we improve selectivity, we expect our process to be better. These contours say, okay, for 80% selectivity and a given primary energy requirement for CO2 capture, I would have to have 25% one pass conversion to break even. So in a way, it's three parameters of the same problem in one graph. Okay, I'm running out of time, so I want to go a little bit into the economic evaluation. So the big lessons from this part so far is that, and again, I would say that this is something that is not appreciated very much. That I would say, most often people will immediately ask the question, does it make sense economically? Before we address this question, you have to ask the question, does it make sense from an energy point of view? So, for this to be energetically feasible, you have to improve one pass conversion, potential selectivity, and technologies for CO2 capture at the power plant. Assuming that this has been done, now we can start asking some questions about economics. So the first bullet really says what I showed earlier. From these mass and energy balances, where we will calculate utility costs and raw material costs, all these things. Then we're going to use some approximations to do some of these calculations very fast. And finally, we're going to have these models that tell us what's the capital cost and what's the energy requirement for each one of these blocks. All of the research, or the most challenging part, is this solar reactor, right? Obviously, that's where the advances are needed, and that's where the research is happening. So for now, I'm going to omit. Actually, it's going to turn out that it's very, very important. But for now, just to discuss some of the trade-offs, I'm going to omit this block. Okay. So what we did this evaluation for many systems, changing one pass conversion and one pass selectivity. And for each combination of the two, we calculated the minimum selling price. So a system today is going to have selectivity 40%, one pass conversion 5%, is greenish. The price is going to be around $1.5 per kilogram of methanol. Unfortunately, the industrial price, it fluctuates heavily, but it's around $0.5 per kilogram. As we start improving one pass conversion, we start moving into the blue. As we improving, one pass conversion in this direction, as we're improving selectivity, we start lowering the cost. So again, today we are somewhere around here. So the points around this line, this contour, would be the points where we break even with industrial practice. What is interesting is that we will become energetically, and as I have drawn two curves here, we become first economically feasible and then energetically feasible. So we would be able to compete with the industrial price before the process produces more energy than it consumes. Okay, so what this graph shows, again, it's minimum selling price. So the lesson from this is that, okay, again, assuming that 0.63, I'm kind of guessing here, is this somewhere here in this third shade of blue. So probably it's going to be somewhere here, or here even. So we have a cheap process, but our process consumes too much fossil energy. This is the lesson. Okay, what can we do about that? Well, we can start trading production of electricity using a natural gas power plant with solar electricity. What happens if we start doing this trade? Our process becomes more expensive because electricity for photovoltaics is more expensive than electricity from natural gas, but our process becomes more renewable. So because of these calculations turn out to be that way, we can start thinking about it. If we were becoming first energetically feasible and then economically feasible, then there wouldn't be any need to do that because the challenge would be economics. Now the challenge is source of energy. So what we are showing here is exactly the same graph, but we have traded electricity generated in a traditional power plant versus photovoltaics. So if we compare the two, really the next graph is more expensive. You see more green in this graph than in the previous one. But what is the advantage? We break even energetically also earlier than before. So the lesson from this study is that, again, especially when we start thinking about these renewable energy systems, is that we cannot be, if our goal should not be only produce something from a renewable feedstock, but we should also be thinking how we're going to be running the compressors that are going to help us do these conversions. The electricity should be renewable. How we're going to be running a distillation column that needs heating. The heating should be coming from solar, and this would help us overall. So I think I'm going, I don't know how much time I have. I think
we've got 20 more minutes total, so you get.
Okay. So what I omitted is the reactor. And this is very expensive. Again, very early stages of research. So the reactor is very expensive because we want to have big area so we can receive a lot of sun. So we will need so what is the reactor? We send in water in the form of steam and CO2, so it's gas, and we want all of this material to see the sunlight, so the conversion happens. So it's going to be something very flat and very large. So the capital investment is going to be very high. Alternatively, we can use concentrated solar energy. then it wouldn't have to be so flat, because if it's concentrated, the temperature is going to be high, the conversions are going to be easier to make, but then we will need a big capital investment in terms of mirrors. So no matter how we do it, building this reactor, this block that was in yellow, again, it's free from an energy point of view, but economically, the capital cost is going to be high. So we try to estimate the cost of this system. And I'm not going to go into the details. The difference from the previous slides is that now we have an estimation of this capital costs for this system. And then the other thing, very important, not very appreciated, is that this system is going to operate only 8 to 10 hours per day. So in general, in the chemical industry, it is what we call capital-intensive industry. Building this facility is very expensive. Then we want to utilize it as much as possible. We want to utilize our expensive assets as much as possible. And with the solar-based technology, this is not possible, because solar energy is available 8, 10 hours per day. So there is nothing we can do about this block. This block is going to be operated 8, 10, 12 hours per day. But maybe we can operate the other systems 24/7. Now, one reason for doing that, or for wanting to do that, is that, again, we are utilizing our assets, and we don't have to over-design them. I'll come back to this point. But also some of these, especially this purification process, are very difficult to turn on and off, because it takes some time to warm up and reach what we call a steady state. And it takes some time to shut them down, and starting them up and shutting them down are very complicated process, labor intensive, and I would say even dangerous. So we don't want to do that. So the question then becomes, can we come up with the configuration that would allow us to operate everything in white 24/7, unavoidably, the yellow only a few hours per day? Yes. This can be done through storage, and this is a little bit more complicated, but I'll try to go through this slide. So what we assume, it was a simple block. Actually, it's not a simple block. It's a little bit more involved than that. We have materials coming 24 hours a day, and they are being stored in this tank. It's going to be an array of tanks, but for simplicity, we have a storage tank. So during the night and day, we are sending material here. We are going through, and these 3 blocks really can be viewed as one block: feed pretreatment, catalytic reaction, catalyst recovery. We are carrying out these things only during the day, and the products go to another storage tank. So the power plant works 24 hours, sends us materials 24 hours. Everything else here operates 24 hours. So during the day, our solar system works very hard and depletes the storage tank during the day. But during the night, this system is not working, and the material keeps coming from the power plant, so the inventory goes up. So it's kind of a periodic operation where during the day, this storage goes up, and during the day goes down, goes up, goes down. And then on this side, during the day, again, our solar subsystem, this guy is working hard, is producing more than what is consumed in C, D, and E, so it goes up. And during the night, we don't produce, we don't have sun. We want to keep running B, C, D, and E, so the inventory goes down. So we have these 2 tanks that connect the discontinuous operation of the solar subsystem with everything else that is continuous. So how expensive is to really run this system? It turns out that it's quite expensive. So when we started the study, we were not thinking that this would be really an important consideration, but it turns out that this intermittency of solar power is a big challenge. Why it's expensive? because in order to maintain operation during 12 or 14 hours of no sunlight, we need very big tanks to store gases, because our products are, or some of our, here we have CO2 that is coming and it's a gas. So either we need very big tanks or we need to compress them to make them liquids, but this also requires a lot of energy. So this turned out to be an important challenge. Now, this is kind of and when we wrote the paper, we didn't want our message to be that. And it was viewed by some colleagues like being pessimistic, but really this is, our view is a little bit different. That's why we do research. So when all these details are taken into account, and really this system, the cost of this system is taken into account, the price goes very high. So this is a logarithmic plot on the y-axis. And this is how good, I will just simplify, how good this block is, which really tells us something about the rate of methanol production per gram per hour, per gram of catalyst per gram of hour. So we are in this, maybe that was 2-3 years ago, maybe now we have pushed the envelope research-wise, we have moved a little bit here, but still our price is in the $10 per kilogram, whereas before it was in the $2 per kilogram. So again, in some ways pessimistic in that we are not at the industrial price that would be there, but on the other hand, nice because there is a lot still to be done from a research point of view. So this shows again the cost as a function of this activity. Then here we have changed, I think I'm going to skip some of these things. I think it goes into the details. I will end with this figure. This is what is called tornado plot. So we studied how improvements in different areas would affect the economics. So in this plot, whenever we chose a base case, and this base case, given certain assumptions, is $5.6 per kilogram of methanol. And this is our base case. And now this plot shows how much the price is going to change if certain parameters are modified. So this lambda is the fraction of operating hours of the solar component. So the lambda can, the price is going to go up if it goes to 12 hours or if it goes to 8 hours. I think we assumed 16 for this system. So as the hours during which the solar component operates decrease, the cost goes up a lot. So why is this? Because again, this system is very, very expensive. And if we utilize it fewer hours, we have made a big investment and we don't reap the benefits of it as the hours of operation go. So that's why this lambda is the most important factor. Then the capital of the reactor, as it goes up by 50% or 100%, is going to increase the price. Then the irradiance, depending where we build the facility, is going to affect the price, utilities, catalyst, land, and then something about the separation. So the big message, again, which confirms what we found earlier, is that really the conversion of CO2 and water, the reactor that is going to convert CO2 and water to our fuel, is the most important component. And I think with that, I'm going to end. This is how we can think about storage, but I'm not going to go through the details. The point is that compression and storage can be quite important. Again, because compressors are expensive to build, the electricity to run them also is going to subtract from the net output of the facility. So what the community in the area of catalysis and reaction engineering, they have moved towards systems that they can run intermittently. And this has its own challenges because the temperature is going to go up and down very frequently, and it's a materials challenge, but there are certain groups that they are studying these systems. So I would say, just to conclude, that what I presented in the first part, it was more, what I presented in the first part was more about general methods to address these problems, and knowing a chemistry or a technology that carry out a chemistry, but building around it a system is what we call process synthesis. So the first part of the talk, I talked a little bit about process synthesis. I didn't cover really surrogate models. And using these ideas, then we studied solar fuels. The take-home messages, we have to capture CO2 in an efficient way. We need better conversions and selectivities. And then we should be using solar energy to produce electricity and heat to be used in our facility. And finally, these are some targets for the researchers in the field. So thank you very much for your attention, and I'll be happy to take it.
So toward the beginning, you didn't show the solar conversion to to biofuels, but that's an even more inefficient process at the beginning, where photosynthesis is 1 or 2% efficient, correct?
Yeah. So the big difference is that, and again, is that this is supposed to be for free. Mm-hmm. That we don't have to do anything. The 1% is very inefficient, but we start paying for biomass, so already the 1-2%, whereas some of the conversions from solar to electricity, yes, it's 30%, but we have paid for the photovoltaics, whether we haven't paid for the lignocellulosic biomass.
Sure.
Which it's debated, and we need more area, so there are other downsides for it.
Was any analysis done for CO2 capture, say converting for solar fuels, another way to do CO2 capture and use it maybe CO2 as a refrigerant?
Yeah.
So was any analysis made for different ways of capturing CO2 and making an end product?
Yeah.
And
so
what are the economics? And then take the approach, what's the best of it?
Yes. So we didn't do it. There are many studies for CO2 utilization, as they call it. So we capture CO2 and we convert it to something valuable. Converting it to something other than fuels is definitely more valuable from an economics point of view. What is interesting there is just the sheer scale of CO2 emissions versus anything else other than fuels. So the CO2 emissions, the tons of CO2 emitted per year versus anything else other than fuel is orders of magnitude higher. So converting it to refrigerant for the first X amount of kilograms of CO2, it would make a lot of sense. But we would flood the market, we would produce as much refrigerant as we need over a year in the first day. That is what makes the problem very challenging. We have to find a CO2 utilization that would kind of match the CO2 production, which is only fuels, really, which makes it economically very challenging because fuels are cheap. And this is something that always is discussed. This is also in the area of biofuels. People are thinking, producing ethanol is not going to beat gasoline. It's going to be more expensive. Can we produce another chemical? And people are exploring that. The thing that we have to keep in mind is also the volume. That we have to find something that is more expensive, so the economics make sense, and it has a big demand, a relatively big demand. So we can use a lot of CO2 towards that.
Can you give me an idea of how, for the intermittent storage problem, how oversized does the system have to be in order to accommodate? Like if you've got, I don't know, if you're just using well, I guess I'll let you answer the question.
So the easy and the nice answer would be obtained if we assume that we need storage for 12 hours. So we can operate during 12 hours, So let's say 6 a.m. to 6 p.m., just to simplify things. At 6 p.m., we need to store material that will be enough for 12 hours of night operation. And at 6 a.m., it's okay if I have zero. I have operated everything else continuously. It's okay if I have zero because the sun will come up. I will start. It's not, unfortunately, because we may have cloudy days, because there are so many things. So I would say maybe 16 hours. We have to have storage tanks capable of holding material for 16 hours of operation. It's a very, and I don't know if that's a good answer. It's a challenging, how comfortable are we at, and what can we do when we see that our tank, so we have a cloudy day, can we shut it down and turn it on the next day, the whole thing? Or maybe not. If that's not so expensive, shutting it down and starting it up, maybe we can be more conservative with the storage. But these would be the things that would go into that calculation, but I don't have an exact answer.
Maybe piggybacking off that, how do you deal with the seasonal variation, and especially because we're here, we go from 8 hours to 16 hours, and from different seasons of sunlight.
So you don't want to design for the sunniest day of all, because then you would make a facility which would be underutilized. So you would go, and we have done some work there, you would go with a design that would be able to harvest 70% of the sunlight, that would be available maybe every month except July and some days in August. So you don't over-design. And the days that you get this, you what they call curtailment, you will just simply focus somewhere else. So the solar won't enter your system because it's going to overheat things. So this is done actually currently in concentrated solar plants. So you don't want to, you are going to, again, come up with a design that is good for 70, 80% of the days, depending, of course, on the geographic location.
I know that in the European Union, the auto manufacturers are arguing for reduced emission standards from engines because they say they're going to reap benefits from producing these types of fuels in the future. And so they're making a policy argument for, I guess, dirtier engines, but maybe in anticipation of cleaner fuels in the future. And that's an argument that's going on now. Do you think that there's enough research out there to support Andrew's position?
I'm not an expert. I don't know. So there is all this community about engine research and studying how different chemicals would burn, how much soot they would form, and all sorts of metrics. It sounds like backwards. Why not do? It seems to be something that would help the automakers, but I think it has to come from different sources. Why not maintain the standards and have cleaner fuels? Is the argument that some of these renewable cleaner fuels would be bad burners, and that's why we have to relax the requirements?
No, I think that they just don't want to tune their engines so much. Produce turbocharge everything, or get the combustion characteristics of the cylinder down to a very fine level of accuracy, and so they would rather have a speculative view of fuel production, but they reap the benefits of not having to invest in cleaner engines themselves now.
Yeah, I think there is probably an argument not so much for solar fuels. For solar, I would think there's going to be something relatively clean, but in the area of biofuels, so there, so far we are exploring, let's say, the conversion of sugars, biofuels into ethanol, which means that we are leaving a lot of components present in the biomass. We burn them because we don't have anything better to do with it. I could see there why one arguing, well, if we start using some other polymeric compounds that we don't currently use to convert to ethanol, and we cannot convert them to ethanol, if we want to use them as fuels, we will have to relax the requirements. I could see that maybe, not so much for solar fuels, but for biofuels.
Yes. One other thing that I've seen kind of going through a lot of discussion on what to do with on the electric grid for days we have really excess solar generation. You know, it might be a spring day where we're not using a whole lot of energy, and a lot of discussion goes to, well, we can just create fuels like this. But it seems like you're going to be wanting to run this plant as much as possible, no matter what, and that's not necessarily tailoring the production to these excess solar days.
Yeah, so very good point. So there is this idea that if we monitor the peak of electricity production, let's say on a hot day, maybe not in Wisconsin in January, it's going to be 2-3 p.m. We have a lot of electricity demand because of air conditioning. And so this matches nicely the availability of solar energy. So the solar energy can be used to meet that peak. But if we want solar energy to penetrate further, we would have to start using solar during the night. And then we go into storing of solar energy. One way to store it is through chemical transformations. So during the day, we have solar energy, we convert it into something, a chemical, and we keep running during the night by burning the chemical. I'm simplifying, but so yes, that's one way to increase solar technologies, power and fuels penetration. And it definitely has its merit, although probably when solar has really fulfilled its potential during the day, and we're not there yet. I think in Germany, they say that there are certain days where during the day they are using only solar. During some hot days, they can meet all power requirements using solar. But I think it's only there, only in Germany.
I mean, there are days where there's so much solar, hitting the system, but the demand is so low that they actually have excess solar. And so that's what do you do with all those excess days to store it up for days where you might need it the extra cloudy day. I think that's a big challenge. Like as we're looking for solar electricity penetration going forward, how can we deal with those really excess days and then really deficit days?
So yeah, and there the conversion to chemical energy is there.
Any other questions? Thank you again for your presentation.
Thanks.